Now what we're going to do is we're going to revisit the matrix vector multiplication algorithms as presented with the flame notation, and we're going to change them slightly. We're going to partition through those matrices differently than we did before. And the reason for this is that this prepares us to talk about how to multiply with matrices with special structure. For example, matrices that are triangular or matrices that are symmetric. So, to motivate what we do, let's consider this concrete example of a 5 by 5 matrix multiplying a vector of size 5, and for convenience we're going to update a vector y of all zeros. Let's re-examine the dot product based matrix vector multiplication. Well, all we did was we marched through the matrix by rows and performed dot products. What if we march through our matrix somewhat differently? And this is going to only work if m is equal to n. In other words, if A is a symmetric matrix. Let's have a look at it. Now this is the way we marched through the matrix when we triangularized or symmetrized matrices in week 3. What do? We expose, and now notice that our row is partitioned into a scalar and the rest of the row, which multiplies this scalar and the rest of this vector x. So we've partitioned our dot product into a scalar multiplication added to a dot product. Then we move forward and we do it again, and now we notice that we have this part of the row, a scalar in the middle, and then this part of the row, leading to this way of computing it. We now have 3 pieces. Okay, and we move forward and we keep doing that. Now this way, we changed the algorithm that we already had for matrix vector multiplication that performed dot products, and we reformulated into one that marches through the matrix and vectors somewhat differently, still performs our dot product, but now partitions it into different pieces. And notice that we've been preparing for this for a while. Back in week 1, we looked at slicing and dicing the dot product. That was in preparation of this particular step. So you may even want to go back and review that video. So why is this alternative way so important? Well, what if A is lower triangular? A typical step in our algorithm would put us in this situation, where now if the matrix is lower triangular, there are zeros sitting above the diagonal. So if we now look at the computation associated with this dot product, what we notice is that this right here always evaluates to 0, so we don't even need to do it. And that saves us floating point operations. What we're going to see is that it's going to cut the number of floating point operations that are required roughly in half. Now let's re-examine the Axby-based matrix vector multiplication. Okay. There we marched through the matrix by columns, and we performed Axbys, and so forth. What if we march through our matrix differently? Well, then we do this, and we go forward, etc. And the important thing here is that each Axby now is partitioned into Axbys with the different parts of the column and the vector, etc. So here is a typical situation. What you notice is that this top part here is just updated by doing this times that plus that. We can express that here. And when we do that, we see that we end up doing an Axby, and a scalar multiplication and addition. That gives us then this algorithm on the right, where we now update separate parts of vector y with separate parts of the current column of A. Why is this so important? Well, again, look at the triangular matrix multiplication, and let's say that we've gotten to this column right here. If you look at this particular part of the Axby, you notice that there is a 0 vector involved, and when there's a 0 vector involved, you don't need to do the computation, and therefore you perform fewer floating point operations when you execute the algorithm. This alternative way of marching through the matrix and vectors sets us up for later discussion about matrix vector multiplications when the matrix has special structure, in particular when it's triangular or symmetric.